So I'm going to talk about the quantum life of pi. Just a brief introduction to myself. My name is Aninda Sinha. I'm a professor of theoretical physics at the Center for High Energy Physics at the Indian Institute of Science in Bangalore, India. And I am also a Quantum Horizons Alberta Senior Fellow at the University of Calgary in Canada. So the title has quantum and pi in them. So I will try to explain what is quantum about pi in my talk. So let's get going. So this was my abstract. So I will talk about an infinite new number of formulas for pi. And these are characterized by an extra parameter, and which I will call an elasticity parameter. And why I call it an elasticity parameter, I will briefly explain. And for large values of this parameter, we will recover a well-known series, which is called the Madava series or the Madava-Leibniz series. And the methods that I will use will also lead to the discovery of an infinite number of new mathematical identities, which are not really known how to prove analytically, but which can be verified numerically using Mathematica. The only way that we know how to prove these identities is via some techniques that we discovered or invented over the last few years. So here is the flowchart of the logic, what we were thinking that led to these discoveries. We were revisiting the origins of string theory. Now, as many of you may know, string theory is a candidate theory for theory of quantum gravity. And we have been investigating string theory for the last 50 years or so. But there are several aspects of the theory that we don't quite understand. Examining these questions led to a paper which was written last year with Arnab Saha, who is a postdoc at the Indian Institute of Science. This was published in Physical Review Letters. And in this paper, we were actually looking for a new representation of the Euler beta function. I will remind you of what the Euler beta function is. The Euler beta function plays a very important role in the origins of string theory. It is the simplest example of what is called a scattering amplitude in that particular theory. And this new representation, in turn, as corollary, led to an infinite number of new formulas for pi with different rates of convergence. Now, I should actually make a disclaimer here that these new formulas for pi do not compete with the fastest converging representations for pi that we know. For example, through the Chudnovsky algorithm. For example, Mathematica uses the Chudnovsky algorithm to calculate the digits of pi. But nonetheless, these formulas are fascinating because they are parameterized by an extra label, which enables us to dial that label for whatever values we want. So one of the reasons why we were investigating this is because we wanted to play around with new ideas for what is called the bootstrap program in physics. And now I will not have time to explain what the bootstrap program is, but I just wanted to put it out there because this was the main reason why we were investigating these new formulas, which in turn gave rise to a new technique, which we dubbed as the stringy dispersion relation. So this is a version of the Cauchy residue formula, which for a function of two variables, it also has an elasticity inbuilt in these formulas. And so, in fact, this is important because if you think about the other famous formulas for pi that form the basis for these fast converging representations, we come across Ramanujan's famous 1914 work, which subsequently led to the development of the Chudnovsky algorithm later on. And so this investigation, we were asking the question, what is the physics behind these representations? What is are there known physical theories which can explain these formulas? And this was published with my graduate student Faizan Bhatt in Physical Review Letters, and this was recently accepted as editor's suggestion. So this Ramanujan's 1 over pi and LCFT is something that I will only briefly allude to at the end of my talk. LCFT stands for logarithmic conformal field theories. There are a special category of quantum theories which we have been studying over the last 3 decades or so. And I should also mention that both these works were presented in the Wolfram community site. In particular, the first work, we are very grateful to the Wolfram moderators who helped us improve the presentation. And I have linked it in my presentation, so if you wanted to have a look, please feel free. So just to tell you a brief history about pi. So there is the series, the first series that is known to us is what is called the Madava series. It's also called the Madava-Leibniz series. So this is an artist's depiction of what Madava might have looked like. He lived in the 14th century, 15th century, and we really don't know what he looked like. He looks like an impressive, confident person. And this was pre-calculus, so calculus had not been invented. So it's a fascinating story as to in what format he presented these formulas. So these formulas were presented essentially in the form of poems. So if you search, you'll find out in what format these formulas were presented. So this is the formula that he came up with. And the things to note about this formula is that they are alternating in sign, and more importantly, it does not have absolute convergence. So if you actually look at the formula, it has 1 over n. So 1 over n, of course, does not converge. But because of this alternating sign, there's a canonical form that it takes, which enables us to calculate digits of pi. And this particular series, which is the first infinite series representation that is known to us, is notoriously slow to converge. You can play around on Mathematica and check how many terms it takes to converge to 10 decimal places, and you'll find that it requires billions of terms. Now, the physics question that we were investigating, on hindsight, what I can tell you is that there is a physics understanding of what this n means. This n corresponds to a picture in string theory, which tells you how fast the string vibrates. And if you actually see the picture of a string, if you have in mind the picture of a string, then you will find that there is some kind of a tension that the string has. So you would expect to see that there must be some information about the tension of the string or the elasticity of the string in the formula, but that is not present in the form that is shown on this slide. So that's a question that you can anchor your thoughts on, that where is the elasticity that the string picture gives us in these formulas? And that is the question that we will find an answer to. So this is the Madava series. So you can play around with what it looks like. So on Mathematica, if you just put it in, ask Mathematica to calculate the first 20 terms, truncating to 20 terms, or so the first 20 decimal places by truncating to 20 terms, you will find that it doesn't even give you the correct second decimal place. So it takes the value 3.18, and so that's an example of the fact that it converges very slowly. Now, the new formula that I'm going to talk about, which actually has in it the Madhava pi series in a particular limit. So this is the simple formula that I showed you in the previous slide, and I've demonstrated here as well, is what I will call a stringy pi. And this formula is presented in this paper that I mentioned. And this discovery was chosen by Scientific American last year as one of the 7 coolest mathematical discoveries of 2024. And the formula looks like this. So even in the Madhava series, the first term, the k equal to 0 term, starts with 4. And this new formula also starts with 4. And now the rest of the terms actually take on a very interesting form. So first of all, there are portions of the formula that you will readily recognize. There are these fractions 1 over n plus lambda. And lambda has a very important role to play in my talk. So note that lambda here, I have not specified what it is. On the left-hand side, there is no lambda. So lambda is this elasticity parameter that I was telling you about. And lambda, you can put in whatever value you want. We will check that in a bit. And so there is this minus 4 over 2n plus 1. And then there is this additional term, which is the Pochhammer symbol. So Pochhammer symbol in this form, where n is an integer. So this subscript n, if it is an integer, then the Pochhammer symbol actually becomes a polynomial. It's a polynomial of degree the same as the subscript here, n minus 1, in the argument that is presented here. So if lambda was a rational number, then each term in this series would be a rational number. So you'd get a new formula for pi for any rational lambda that you choose. So there is a condition for lambda. So the real part of lambda has to be bigger than, in this particular representation, bigger than minus 1. There are analogous representation where the real part of lambda is bigger than 0. They have some minor differences. So those formulas can be found in our paper. So the key thing is this lambda. So as I said, the real part of lambda needs to be bigger than minus 1 in this representation. So you can put in lambda to be a complex number as well. And for even for complex values, it converges to pi. So if you now truncate the series, suppose you truncate it to 10 decimal places and you put in a complex number, then you will see an imaginary part, but the imaginary part becomes smaller and smaller the more number of terms you retain. If lambda was real, then you would get a real number, and that also gives you pi the more number of terms you retain. So for example, you can do some nice checks in Mathematica. So you can check the convergence of this series. So here I have given you the code. So in fact, I should tell you that I had fun using ChatGPT 5 to write some of this code, because ChatGPT 5 is not very good in writing codes for Mathematica, but some of the things it can do. So for example, you can actually check. So here, let me just go through the code with you a little bit. So if you truncate to a particular number of terms, then the partial sums. So the first entry in the argument will be the value of lambda that you're choosing. The nmax tells you the number of terms in the series that you're truncating to. And then we are specifying a working precision as well. So the partial sum for pi, so I chose some random value of lambda, 510 divided by 9. I chose 20 terms and I chose the accuracy of 20. It actually gives you a convergence, at least the 5 decimal place, or rounded off to 6 decimal place. It is correct. It is the expected value that you have. So the expected value is 3.141596. So up till that, it agrees. So this actually converges pretty fast. So remember that in the Madava series, 20 terms didn't even converge to the second decimal place. And then you can choose lambda to be large. Now then actually you start recovering back the Madhava series form. So in fact, that is something that by staring at this formula, you can kind of anticipate, but you can use Mathematica to do a series expansion of this form and convince or get the form of the Madhava series back. So if you actually truncated in n and then you chose lambda to be very large, you do a series expansion, you will find that you get exactly the summoned in the Madhava series. So we can check the accuracies as well. So you can calculate the error and the number of digits of accuracy that you get. So for example, so this is code that is available for anybody to play around with. You will see that if you truncate to 30 terms and you retain lambda between minus 0.9, so as I said, the real part of lambda here has to be bigger than minus 1. And I just chose lambda to lie in this between minus 0.9 and 5. On the y-axis, you see the accuracy, and on the x-axis, you see that I'm dialing lambda. So in fact, this one, there's a typo here. It's not 5, it's minus 0.9 to 125. So as you can see, the accuracy actually shows an interesting behavior. So accuracy becomes worse as you dial lambda to bigger values, but for lambda around the value of truncation, the number of terms that you're keeping in your series, the accuracy is very good. So the y-axis is actually plotted as a minus log 10. That is why you see 5 and 10. So this is actually to the accuracy of 10 to the power minus 5, 10 to the power minus 10, and so on. And then you can do some cool, nice 3D plots as well in Mathematica. So this is, for example, if you wanted to actually keep the number of terms in the series and lambda as tunable parameters, and you want to see how the accuracy behaves as you change lambda, you can play around with this 3D shape and see that it has various valleys, various interesting features that are very difficult to study analytically, but numerically you can play around and see where the best rate of convergence is found. So in fact, if you look at the plot by adjusting it so that your number of terms, so the number of terms in the series is on the x-axis and lambda is on the y-axis, it takes on some interesting shape. It is suggesting that there is an optimum value of lambda which gives you the best accuracy. So you can actually follow the landscape on this plot, and along the landscape, along this curve, you get the best accuracy, and the accuracy actually starts becoming badly elsewhere. So let me actually tell you a little bit about what we were trying to do. So we were trying to find a new representation for the Euler beta function. And that is what led to these formulas for pi. So a little bit of a history. So Euler was a very famous mathematician. He should be an inspiration to a lot of people. And he invented a huge amount of mathematics. He invented what we call E now. He invented, sometimes this is called the most beautiful formula in arithmetic, e to the power I pi plus 1 equal to 0. He invented the gamma function, and he also invented the beta function. This is what the focus is. The beta function is a particular ratio of product of two gamma functions divided by a gamma function. He also invented the Euler zeta function, and the Euler zeta function, when you actually consider it in the complex plane, it becomes the Riemann zeta function. And what is probably not that well known is that he popularized the notation of pi. And he's also an inspiration because he went blind towards the end of his life. He lost his house in a fire. Then his wife died. But in spite of all these obstacles, his productivity increased. And his productivity was so much that at the end, he produced 25,000 pages of maths. And his work continued to be published 50 years after his death. So the picture here, which actually shows this blue blob and two lines coming in and two lines going out. So you need to read the figure from left to right. So this is an example of what is called a Feynman diagram. And in the particular context of string theory, this represents two strings coming up, joining up, and then splitting and becoming two strings again. It is called the 2-to-2 scattering amplitude. This Euler beta function is the representation of that particular scattering amplitude. Amplitude essentially means the probability that two strings come in and two strings go out in a very specific way. And the arguments of the Euler beta function in string theory get related to the energy and the exchanged energy of the two incoming particles or incoming string states. And the reason why the Euler beta function becomes pi is because gamma of half is basically square root of pi. So if you put x equal to half, you are supposed to get pi at the end. So once we find a new representation for this Euler beta function, the formulas for pi will come out as a corollary. So what are the properties of the Euler beta function? So the Euler beta function has poles when x or y are negative integers. But if they are both negative integers, then you don't have a double pole or a pole at double values because it is divided by gamma of x minus y. So the second pole actually cancels and you only get one set of poles. And there are some standard series representations. So we'll verify the standard series representation in Mathematica in a bit. So, for example, the Euler beta function takes on this form that it's an infinite sum. It's 1 over n factorial, and then there's this Pochhammer symbol, which is again a degree n polynomial in minus y plus 1. And in this way, in this formula that I have presented here, the poles in at x equal to minus n are manifest, they are visible. So in Mathematica, if you put beta of x minus y, so this is the Euler beta function that is represented in Mathematica, and you can do this infinite sum n equal to 0 to infinity analytically in Mathematica. And if you use full simplify, it is going to tell you that it is in fact the Euler beta function. So this is a representation of the Euler beta function. However, this is a little misleading for the following reason, because in doing this infinite sum, Mathematica has actually done an implicit analytic continuation, because this formula does not make the poles in y manifest. The poles only in x, they are manifest. So for example, if you look at the truncated sum, which does not know anything about the poles in y, and you compare it with the expected value, you get a y divergence. So here is an exercise that I've done. So this is a difference between the Euler beta function, and I've truncated the infinite sum presented here to 50 terms. And I'm looking at the value of the difference close to a y pole. So if it was true that the truncated sum was a faithful representation of the Euler beta function, you should get something that is close to 0. But you don't, you actually get something that is very big. You get minus 34.11. And that is indicative of the fact that this series is not a faithful representation unless and until you do something more. And that something more is this analytic continuation that is implicitly done on Mathematica. So the question that we try to address in this paper was, is there a representation for the Euler beta function which manifests the poles in both variables? So here I've rewritten the Euler beta function in a sort of a conventional way that is usually presented in the string literature. I've replaced x and y by minus s1 and minus s2. This is this new formula which actually makes manifest the poles in both variables, s1 as well as s2. Here is this extra term 1 over lambda plus n. So there is this parameter, again, because of the string picture, the string has elasticity. So there must be some stretching going on. So there must be some information about how stretchy the string is. So this lambda you can think of as the elasticity parameter. So this is the representation for the Euler beta function. The point is that you can truncate this infinite series and still retain the physics that is behind the string picture that we have. So in this particular case, in this formula that I have presented here, this is a representation of the Euler beta function itself. Here you require the real part of lambda to be bigger than 0. So in the previous formula, I told you that there are various formulas that one can find. In the previous formula for pi, we need a real part of lambda to be bigger than -1. And the difference arises because in the previous part, I was actually using the amplitude for superstring theory. Here, I'm just using the formula that for the Euler beta function, which is actually a bona fide amplitude in bosonic string theory. The point about this formula is that each part of the formula, so for example, the poles in the S1, the poles in S2, and also this extra piece, lambda plus n, they converge on their own. So here is a check. So for the same check, so we are looking at the new representation, subtracting off from the beta function, and we are looking at it close to the same value where the other representation did not work so well. And now you find that indeed it gives you a value that is close to 0. So remember that previously we saw that it was close to -34.11, which was a terrible representation in that sense. So you can also dial lambda, and you will find that, again, similar to the representation for pi, it actually agrees well at certain, it converges much faster for certain values of lambda, and as you dial lambda to be larger, then the convergence becomes worse. So here I have not shown you for very large lambda, but eventually the convergence is going to become bad. You can also do some check, and this is how we do sanity checks in theoretical physics. We sort of have a formula, and then we go to Mathematica just to do some sanity checks. We put in random values. So we put in random values for the argument, and we ask what is the fractional difference. And we do it for whatever number of points. Here I have actually shown you an exercise with just 50 points, and you will see that the first arguments are the points, the x and y values, and then the difference, the fractional difference, is the third entry in this array. And as you can see that all the array entries are very small. So here you get again an infinite number of new bizarre looking identities. In what way? Because of the fact that you have this new parameter. So if you actually do a series expansion of the Euler beta function around x and y to be 0, you will get the Euler zeta function. So for example, if you look at the coefficient of y square as a series expansion, you will get zeta 3. This new formula, new representation with the Euler beta function with the lambda, the elasticity in the formula, actually gives you a new formula for zeta 3. And the new formula for zeta 3 can be easily again found using the series coefficient inbuilt function in Mathematica. And you will find that again, it actually converges pretty fast. But what you can do is you can now take the derivative of this new representation with respect to lambda. So here we are taking the derivative with respect to lambda. And if you are looking at, because the left-hand side does not depend on lambda, the derivative with respect to lambda has to go to 0. And so you can actually do this derivative. You'll get some very complicated identity involving polygamma functions. And it should go to 0. And you can actually check that numerically. It's very hard to prove this analytically from first principles without actually invoking the new sort of tools that we invented. But you can do checks on Mathematica to actually verify many of these identities. So in the last minute or so, I will actually tell you very briefly about Ramanujan's pi. In 1914, Ramanujan published a beautiful paper, which you can easily find online. You can get the PDF version, where he presented 17 remarkable formulas, not for pi, but for 1 over pi. And this is what inspired the Chudnovsky brothers' algorithm, which now forms the basis, and this is even in Mathematica, to compute many digits of pi efficiently. And in this new paper, which I told you about, we asked if there was a physics connection. And there is indeed a physics connection. In fact, the starting point for the Ramanujan's pi derivation was this relation called the Legendre relation, which looks like this. So F sigma in this relation is a particular hypergeometric function. It's a Gauss hypergeometric function. In the next code, I will show you what precisely this formula reads. So in fact, you can play around on Mathematica and check the accuracy of this formula. You can put pi by sine pi sigma on the left-hand side. And as you see that Z can take on any value that you want, sigma can take on any value that you want, and you still get an identity of this kind. And again, analytically, it is not that easy to prove this, but numerically you can verify it. That again, I have chosen some random values for Z and then some random values for sigma, and the ratio of both sides just gives you 1. So we asked, is there a physics connection? And the way that we discovered this physics connection is that this combination, so in the Legendre relation, you see the product of two hypergeometric functions, and then there is a derivative here. So it turns out that this combination of these Gauss hypergeometric functions occurs in many interesting areas of physics. And this includes logarithmic conformal field theories, black hole physics, and even cosmology. And I can safely say that we only scratched the surface, and there are a number of math-driven questions that are waiting to get a physics answer. So we need to understand the physics side of it much better. But for sure, the Wolfram language has served as a sanity check for mere mortals like me. So I'm not a genius like Ramanujan, but the Wolfram language has provided a bridge. And in fact, just to conclude, I have used Mathematica since 2001. And for a theoretical physicist like me, Mathematica provides the lab. So it's without this lab, it will be very difficult to get intuition. The new formulas we discovered relied crucially on both numerical and analytical checks, which were performed using Mathematica. And I did not have time to elaborate on this physics connection on this Ramanujan pi series. But I should also point out that there is a beautiful blog by Stephen Wolfram about Ramanujan and his time in Cambridge. So if you have not seen that, I strongly encourage you to read it. So I'll stop there. Thank you for listening. Yes, so there is a question on the chat. I will read out the question. Are the new series somehow asymptotic with respect to lambda? So they are not asymptotic if you actually, if you look at the formula for pi, if you actually make lambda bigger and bigger, the terms literally go over to the same terms as the Ramanujan pi series. So in that sense, you get two interpolating features. So on one side of the interpolation, it's converging very fast, and then there is a transition where the convergence becomes bad, but then ultimately it actually maps over to a known series, which is this Madhava series. So if I use the word Ramanujan pi series, that's not what I meant. I meant the Madhava series for large lambda. So, okay, so I don't see any other questions. So thank you very much for your attention.